Welcome to the icy frontier where the Antarctic tundra keeps secrets that would blow your mind. In the next few minutes, we'll roll through 5 astonishing facts that turn this frozen desert into a goldmine of wonder. Fact number 1: Hidden rainfall. While the world pictures Antarctica as bone dry, summer storms actually dump measurable rain on pockets of the tundra, a rare oasis in the most arid place on Earth. Fact 2: Dives beneath the ice, subglacial lakes. Hidden beneath miles of frozen crust, these liquid reservoirs stay liquid, warm enough to sustain microbes that have been locked away for eons, a living time capsule. Moving on, Fact 3 showcases wind-powered snow sculptures. The relentless katabatic winds sweep across the plain, carving ever-changing patterns, nature's own 3D printer, sculpting snow into fleeting masterpieces. Fact 4 reveals ancient meteorite fields. The continent's dryness preserves a staggering number of space rocks, each a relic older than our own rocks, scattered like glittering breadcrumbs across the ice. Finally, Fact 5 is the extreme day-night switch. In the polar summer, the sun never dips, triggering continuous photosynthesis in hardy lichens that cling to rock, turning daylight into a non-stop growth marathon. These facts barely scratch the surface of what lies hidden beneath the white veil. But that's just the beginning. In Part 2, we go deeper into the science, the explorers, and the untold stories that make the Antarctic tundra a living laboratory of extremes. Stay tuned, because the next chapter will flip everything you thought you knew about the frozen world upside down. Welcome back to our deep dive series on the Antarctic tundra. In Part 2, we traverse the layered chronicle of human discovery, the relentless mechanics that carve this stark landscape, and the hidden biosphere that thrives beneath the ice. The story begins with the heroic age of Antarctic exploration. In 1899, Norwegian explorer Karsten Borchgrevink anchored at Cape Adare, noting for the first time a strip of exposed ground that he called a tundra. His observations were rudimentary, but they sparked curiosity among later expeditions. Fast forward to 1911, when Robert Falcon Scott's Terra Nova team trekked inland, recording the extent of ice-free terrain along the Ross Sea coast. Their sketches, though imprecise, revealed a narrow coastal fringe stretching roughly 100 kilometers, punctuated by rocky outcrops and wind-scoured soil. These early records laid the groundwork for the aerial reconnaissance that would follow. In 1946, the U.S. Navy's Operation High Jump deployed aircraft equipped with photogrammetric cameras, producing the first systematic topographic maps of the continent. The resulting images illuminated a pattern. The tundra was not a continuous belt but a mosaic of isolated islands of ground, each shaped by local microclimates. Understanding how this mosaic forms requires a look beneath the surface. The Antarctic continent is dominated by katabatic winds, gravity-driven flows of cold, dense air that accelerate down the interior slopes toward the coast. These winds can reach speeds exceeding 150 km per hour, eroding snow, redistributing fine sediments, and exposing underlying rock. Meanwhile, permafrost, ground that remains frozen for at least 2 consecutive years, acts as a rigid scaffold. In the Vestfold Hills, a series of research stations established in 1994 uncovered cryoturbation layers up to 30 centimeters thick. These layers bear witness to repeated freeze-thaw cycles that churn the soil, creating subtle undulations and influencing water retention. Subglacial meltwater also plays a decisive role. Satellite gravimetry from the GRACE mission, analyzed in 2018, detected localized uplift beneath the Weddell ice sheet. This uplift is attributed to basal melting, where ocean-derived heat melts the underside of the ice shelf, releasing water that can percolate upward in carved new tundra expanses. Such processes are not static, they respond swiftly to atmospheric warming, making the Antarctic tundra a sensitive indicator of climate change. Beyond geology, the tundra hosts a surprising array of life. Lichens of the genus Usnea and mosses such as Polytrichum cling to the scant soil, photosynthesizing under extreme UV radiation. The most conspicuous inhabitants are Adelie penguins, which establish breeding colonies on ice-free outcrops. A 2022 DNA metabarcoding survey revealed over 200 microbial taxa, many of which are endemic to this environment and capable of metabolizing frozen organic matter. These microbes participate in carbon cycling, slowly releasing greenhouse gases over millennia, a process that could accelerate as permafrost thaws. The scientific community now recognizes the tundra's pivotal role in global systems. The Scientific Committee on Antarctic Research (SCAR) has launched a multi-year program to install permanent ecological plots across the continent. These plots will monitor temperature, moisture, and biological activity, providing high-resolution data on how warming trends reshape the tundra's composition and function. By integrating satellite observations, autonomous drones, and on-site sampling, researchers aim to predict feedback loops that may influence sea level rise and atmospheric chemistry. In summary, the Antarctic tundra is a dynamic frontier where history, physics, and biology intersect. From the daring voyages of the early 1900s to cutting-edge molecular techniques, each layer of inquiry uncovers deeper complexity. As we stand at the threshold of unprecedented climatic shifts, the insights gained from this frozen plain become ever more critical. Stay tuned, because in Part 3 we uncover what mainstream sources won't tell you. Imagine stepping onto a frozen desert that stretches beyond the horizon, where the wind whispers secrets older than any civilization. You think you know Antarctica, an endless sheet of white, a place of desolation. But hidden beneath that stark silence lies a story the world has barely begun to understand. Our journey begins with an anomaly spotted by a weather satellite in 2018, a faint, pulsing glow flickering beneath the surface of the Antarctic tundra. At first, scientists dismissed it as a sensor glitch or distant aurora. Yet the pattern persisted, growing brighter each winter month, as if the Earth itself were breathing. What could cause such light in a realm where sunlight barely touches the ground? The answer emerged from a trio of daring expeditions that braved the brutal cold to drill holes deep into the ice. They uncovered a network of geothermal vents, pockets where molten rock pushes upward, warming the surrounding snow. These vents release mineral-rich steam, nurturing tiny life forms that emit bioluminescence. The result, an invisible tapestry of light, dancing beneath the ice, invisible to the naked eye but undeniable in the data. But the mystery deepened. When researchers retrieved ice cores from the most active glow zones, they discovered thriving colonies of extremophile microbes. These organisms, unlike any found elsewhere, extract energy from the chemicals spewed by the vents, not from sunlight. They produce a natural glow, turning the dark tunnels into corridors of emerald and sapphire. This hidden microecosystem rewrites what we believed about life's limits, suggesting that even the harshest corners of our planet can harbor vibrant communities. The plot thickens with the appearance of the Crimson Glacier, a striking streak of ruby-red ice that materializes only during the longest polar nights. For years, explorers thought it a trick of light, a reflection of the sun on sea ice. Recent analysis, however, reveals that mineral-laden runoff from secret subglacial lakes mingles with the bioluminescent microbes, staining the ice a deep, blood-red hue. This phenomenon not only challenges our visual expectations but also hints at complex chemical interactions occurring far beneath the surface. Each revelation peels back another layer of the Antarctic's secret identity. From silent, lifeless void to glowing underworld, to a crimson spectacle that appears like a warning sign, the continent is far from the barren wasteland we imagined. The frozen tundra is a living laboratory, a reminder that nature's ingenuity knows no boundaries. So why does this matter? The mechanisms that allow life to thrive in extreme cold could inform the search for life on icy moons such as Europa or Enceladus. Understanding these hidden ecosystems also reshapes climate models, as the geothermal heat source may influence ice melt rates more than previously thought. The Antarctic tundra, once dismissed, is now a frontier of scientific discovery, holding clues to both our planet's past and the possibilities beyond it. As the night deepens and the wind continues its endless chant, the truth behind the Antarctic tundra becomes unmistakable. Mystery resides where we least expect it, waiting for curious minds to illuminate the darkness. Now that you know the truth, Part 4 will change how you see this forever. Welcome to the final chapter of our Antarctic Tundra series, where we synthesize decades of research into one definitive narrative. The story begins with the continent's tectonic exile from Gondwana, a journey that set the stage for relentless cooling and the birth of a unique ice-free fringe. As the ice sheets thickened during the Oligocene, ancient temperate ecosystems were squeezed into narrow bands, leaving behind a fossil record of pollen and spore that whispers of a greener past. Fast forward to today, where life clings to the edge of existence through a suite of extraordinary adaptations. Cryoconite holes become miniature ecosystems, harboring bacteria that harness sunlight and organic matter in a perpetual freeze-thaw dance. Wind-driven katabatic currents redistribute heat, carving microhabitats where mosses and lichens eke out growth in the brief Antarctic summer. These organisms, though sparse, drive the tundra's albedo feedback, amplifying local warming and influencing global climate patterns. Historical expeditions have illuminated these processes. The British Antarctic Survey's late 1970s Dry Valleys project uncovered ice cores that traced atmospheric carbon dioxide across glacial cycles, while the 2002 Japanese team recorded an unprecedented cyanobacterial bloom, revealing the tundra's capacity for rapid biological response. In 2021, a multinational consortium deployed UAV LiDAR to map terrain roughness, correlating subtle topographical variations with biodiversity hotspots. Yet the future remains contested. Climate projections suggest a significant contraction of ice-free land, igniting a debate between scientists who predict a surge in primary productivity due to longer melt seasons and those who warn of irreversible carbon release as permafrost thaws. The stakes extend beyond academia. They influence sea level forecasts and inform policy under the Antarctic Treaty System. In this payoff video, we have traced origins, mechanisms, real-world observations, and the contentious horizon ahead, delivering the most comprehensive insight into the Antarctic tundra. If this series gave you value, subscribe. More deep dives coming every week.